Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Lecture 3, Week 1 of Dynamic Atomic Force Microscopy Methods. In the last class, we had started talking about a little more detail about the transient response of point mass oscillator models of AFM probes. You may recall that we talked about the fact that when you do transient motions, you have this decaying envelope that when you ping the cantilever, it has an oscillatory decay unless it is overdamped, in which case it just decays without oscillating too much. And then we moved on in the last class to extending the point mass model to excited cantilevers, and we talked about directly excited systems such as magnetically excited or photothermally excited, where the force is applied on the cantilever directly without moving the base of the cantilever. On the other hand, we had acoustically or inertially or ditho-piezo excited cantilevers, where instead of applying a force directly in the cantilever, the base of the cantilever is actually moved up and down. And we talked about the fact that in the spirit of these accurate point mass models, one could come up with an equivalent effective point mass model for the excited oscillator as well. The equivalence principle was again based on this energy principle, in that if you took the actual cantilever probe and had these distributed forces acting on it, magnetic forces making it oscillate, at the end of the day, if the work done by all the applied forces in moving the tip up and down with a certain oscillation amplitude, if we can equate it to the work done by an effective force in the point mass model to move the tip up and down by the same amplitude, then we've got, based on this energy equivalence principle, a pretty accurate model of the actual probe. Now, we had talked about the fact that when you deal with excited cantilever probe models, there are two distinctions that need to be made. In the case of directly excited cantilevers, there is not too much of a difference between the things are pretty normal in the sense that the force is applied on the tip, and then the base is fixed, and the cantilever just oscillates. On the other hand, things start getting a little complicated for ditho-piezo excited systems or acoustically excited cantilevers for two reasons. First of all, as I mentioned, instead of a direct force, what we actually apply is a displacement. We move the base of the cantilever up and down, or in other words, if you've got a point mass oscillator model, you move the support location of the spring up and down. That's one problem. The second difference is that when we use the optical lever method, we actually end up measuring, in the case of acoustically excited cantilevers, we don't measure the absolute displacement of the tip, Q, but rather we end up measuring Q sub rel, which is the deflection of the tip relative to the base, because what we really measure is the bending of the tip relative to the base. Remember, what happens in acoustically excited cantilevers is the base is moving up and down as well, so the rotation of the cantilever is really related to the tip displacement minus the base displacement, which is Q rel. But we had not really started discussing the solution to the equations governing the excited cantilevers. So that's what we're going to focus on today. And we'll start with response of directly excited AFM cantilevers. And what you see on the top left is a typical image. In this case, we're showing magnetic excitation, but really any form of direct excitation would be valid. And we're going to replace the situation, the figure shown on the top left, by an equivalent rigorous point mass model that is equivalent in many respects to the original actual probe. And, here we have Newton's laws applied to the point particle and the equations of motion written down in 1, where there's an equivalent effective force, external force, F external, which is a function of time acting or applied on the oscillator. The natural frequency of the oscillator is omega naught, and it has a natural Q factor that we have talked about before, and the excitation frequency is omega. Now, frequencies are in radians per second, so they're angular frequencies, and we talked about the fact that we're going to interchangeably shift between Fs, which are the frequencies in hertz, and omegas, that are the frequencies in radians per second. In this case, the measured motion is going to be q of t, which is the tip displacement, and the drive or excitation frequency need not be the same as omega naught. Now, going back to your basic theory of ordinary differential equations, when you have a linear differential equation like this, and you have a excitation term on the right-hand side, we call it a non-autonomous ordinary differential equation, which generally has two components to the solution. There is a homogeneous solution, which is the solution of the same diff EQ without the excitation on the right-hand side, and there is a particular solution, which is a solution with the excitation on the right-hand side. Now, if you go to the appendix, you'll see a derivation of how you get the particular solution and the homogeneous solution. But the homogeneous solution in this case, not surprisingly, is exactly identical to what we had derived in the last class on the transient response. So we'll focus today on the particular or the steady state response. So the steady state response is given by equations 2 and 3 that are shown in this blue box, where the first equation is the steady state amplitude A divided by F naught divided by K. F naught is the amplitude or magnitude of excitation. And on the right-hand side, we have this quantity R. R is the ratio of the excitation frequency to omega naught, the natural frequency. So we call this quantity the magnitude of the transfer function because it, in a sense, captures how the amplitude of the probe responds to unit input magnitude of force F naught for different frequencies. And we know what we might expect, that for unit magnitude of excitation force, if the excitation force is slow and is a lower frequency compared to omega naught, you'll expect a certain amplitude of oscillation. On the other hand, if the excitation force is at frequency omega naught, this magnitude becomes larger. So it kind of refers to, if you will, a ratio of output to input of this oscillator. Output measuring the amplitude, input in some sense measuring a measure of the force applied to the oscillator, which in this case is F naught divided by K. You also see an expression for the phase lag phi. Now, it's important to emphasize that when you're looking at the solution for the particular equation, we are going to write it as A sine omega t minus phi. So there's a minus, which means that we're assuming that the response is going to be a little delayed or behind time compared to the excitation. And with that convention, phi then is going to refer to the phase lag. Had we written this solution as omega t plus phi, in that case, phi would have been the phase lead. Since we have written it as minus, we're defining the sign convention for phase so that phase lag is what phi represents. The homogeneous solution, on the other hand, is shown below. It's the same as what we derived in the last class. And so when you put it together, the general solution of this equation is going to consist of a steady state amplitude and phase lag relative to the excitation force, plus a decaying envelope. And so you can imagine what's going to happen is when you take the probe and excite it, the decaying transient solution dies out in about 1 over q or 2 over q in those number of oscillations, or in q number of oscillations, but the steady state oscillation, the particular solution stays on forever. So let's take a look at the characteristics of the steady state amplitude and phase of the response of this directly excited probe. On the top left, I've again written the magnitude of the transfer function. Again, transfer function is basically a way of describing the ratio of output of the system to input, right? It's a technical word. I just want to clarify that it's not more than what it states in these equations. And when I plot the magnitude of the transfer function as a function of the R, which is the ratio of drive frequency to natural frequency omega naught, I do it for different values of Q. So I've got Q equal to 2, Q equal to 10, and Q equal to 50. And you can see what ends up happening is as Q increases, you see that a more and more distinct sharp peak emerges. And the higher the Q, the sharper the peak is going to be. The narrower the peak, the higher the peak is going to be. But there are a few important things I want to highlight about this amplitude response, or what we call magnitude of the transfer function. The first is that the peak, if you look at what's the value of R at which you hit the peak, it seems to be that the peak, you hit the peak when R equals 1. R equals 1 is when excitation frequency equals omega naught. However, if you look a little carefully, especially at low values of Q, like the one at Q equal to 2, you actually find in this case that the peak value occurs, peak amplitude occurs at a frequency just below omega naught, a little below omega naught. So it's not exactly that omega equals omega naught means you're at the very top of the peak, resonance peak. Let's look over to the right-hand side. On the right-hand side, you've got the phase lag plotted as a function of drive frequency. And one of the key conclusions here, if you look at the formula on the top, is that whenever R is going to be equal to 1, the phase lag is always going to be 90 degrees, regardless of the value of Q. So what that means is this is not an approximation in that you could have any amount of Q equal to 2 or 100 or 1000, but when omega equals omega naught is when the oscillator is exactly 90 degrees, has a 90 degree phase lag with respect to the excitation. The other important thing to notice is when you go back to the left-hand side and look at the amplitude response, or the gain of the transfer function, what you see is that this peak, which appears pretty symmetric at first, when you move away from the peak and go a little bit to the sides of the peak, so to speak, the foothills of the peak, you find that this peak is not symmetric about omega equal to omega naught. In particular, you find that the amplitude of response when the drive frequency is larger than the natural frequency is actually a little lesser than the response when your drive frequency is below omega naught, or when R is less than 1. The other important result that emerges from this is if you look at the value of the y-axis on the graph on the left, the magnitude of this peak is actually, just by looking at it, it almost seems equal to the value of Q. So if you look, for example, at the golden colored curve at the bottom, its peak value is roughly around 2 on the y-axis. You look at the green curve, its value is about 10, which happens to be the Q factor for that curve. And if you look at the magnitude of the peak here for the red curve, you get a number of 50, which is basically the Q factor. So what this is suggesting to us is that this ratio, the amplitude times K, which is the effective stiffness, divided by F naught, is actually, when you're exactly at resonance, omega equal to omega naught, pretty much equal to Q. And you can figure that out by simply looking at the expression on the top left and setting R equal to 1. And you do in fact find that this ratio is not exactly equal to Q, but very close to Q, or approximately equal to Q, especially when Q is very large. And you can look at the appendix for a little more detail behind this. But it's pretty important to note that when you're at high Q, or when Q's are larger than 10, for example, you can pretty much assume that the magnitude of the driving force, or the excitation force, when you're at resonance is going to be equal to K times the amplitude that you're driving it at, divided by the Q factor. And this is going to be a relationship we'll use pretty often as we go in the remainder part of this class. Let's now take a look at the acoustically excited cantilevers. Now, the equivalent point mass model for the system is shown on the top, and the equation of motion was derived the last time, which is equation 5 shown here. However, as I mentioned to you, what we measure in acoustic mode AFM is Q relative, not the Q absolute. So we measure the relative motion of the tip relative to the base. And so we make a substitution of Q equals Q rel plus Z base, which is Z base is the effective base motion. And we put this into equation 5, and we derive a new equation for Q rel, because really it's Q rel that we observe from the photodiode. When we put that in and derive our equation of motion, you can look at the details in the appendix again, but we assume that the base motion is going to be Z naught times sine omega t. Z naught is the magnitude of the effective base motion. Remember again that these are effective quantities. They're not going to be the real quantities that you might measure in an experiment, because these are effective or equivalent values for a point mass oscillator model, not for the actual beam of the AFM cantilever. So Z naught is the equivalent base motion of the cantilever, and the measured response is going to be A sine omega t minus phi subacoustic, where phi subacoustic is now the phase lag due to acoustic excitation. And the results are shown in the appendix, or how to derive them, but we come up with two very nice expressions out of this. One is this ratio, amplitude ratio of A to Z naught, which is the measured amplitude from the photodiode of the tip oscillation to base motion of the cantilever. That's equation 6. It's written out in terms of the Q factor, and R, which is the ratio of the drive frequency or excitation frequency to omega naught. The second is the phase of the measured response of the cantilever relative to, with respect to the base motion of the cantilever. So equations 6 and 7, just by looking at them, are very different in form and dependence on R compared to the directly excited cantilevers. And let's plot out a few example cases. On the top left, I've written out this amplitude ratio, or the magnitude of the transfer function, for acoustically excited cantilevers for 3 different values of, and the ratio is plotted for 3 different values of Q factors, 2, 10, and 50, as you can see. And on the right-hand side is the phase lag of response in degrees, plotted as well for 3 different values of Q. Again, what one notices is, on the face of it, things are pretty similar. As Q goes up, this peak becomes narrower and goes higher. It's the amplitude ratio. But if you look a little carefully, the peak is not located at R equal to 1 exactly. At very high Q values, it does appear to be dead on 1, but as Q goes down, especially if you focus on Q equal to 2, you actually find that the peak of the amplitude occurs, the measured amplitude occurs at frequency slightly larger than omega naught. And this is again described in the appendix in some detail. The second important thing to notice is, if you look at the right-hand side of the phase response behaves in a pretty different manner compared to in the directly excited case. There are differences at the low frequency end. So when you go from drive frequency anywhere from 0 hertz to about omega naught over 2, you find that the phase lag behaves in a very different manner compared to in the case of directly excited cantilever. But nonetheless, we find that the phase does reach approximately 90 degrees of phase lag when R equals 1. Now remember, in the case of directly excited cantilevers, this was exact. Regardless of Q, you reach 90 degrees phase lag when R equals 1. However, in the case of acoustically excited cantilevers, you reach phase lag of 90 degrees at R equal to 1 in an approximate sense. When Q becomes very small, like when Q becomes 2, for example, you find that the phase lag at R equal to 1 is in fact a little larger than 90 degrees. The other important thing we notice is that if you go back on the left-hand side and look at the amplitude response, it again is not symmetric about R equal to 1. As you move away from the peak to the sides, again to the foothills of the peak, so to speak, you find that in this case, in acoustically excited cantilevers, the measured amplitude of the response is larger when you're above resonance as compared to below resonance. That's an asymmetry that comes out. And the second important thing that you notice from the graph on the left is that if you look at these amplitude ratios, again, the numbers you get at the peak values are actually very similar to the Qs that we used for the plotting. So for example, if you look at the red curve, this amplitude ratio is roughly 50. If you look at the green curve, the amplitude ratio at the peak is roughly 10, and similarly for the golden colored curve is roughly 2. And this can be seen if you look at the equation on the top left and set R equal to 1, you'll actually find that this ratio A over Z naught is actually very close to Q when you go to large values of Q. And this is again described a little more in the literature. So this leads us to a very important approximation that we will use later on in the class, which is that if you want to know what is the effective base motion in your point mass oscillator model, all you need to do is go to set the excitation frequency equal to the peak frequency and measure the amplitude that you're getting out of the photodiode and divide it by the Q factor, and that gives you basically the base motion. So this is a very important result that we're going to be studying later and using later in class. Now, finally, I want a quick focus on, we've been talking about phase lead and phase lag, so let's switch to a slightly more practical issue. An important question to ask is, how do you know if your AFM system is plotting phase lag or phase lead? And because many AFM manufacturers don't tell you if it's lead or lag. A simple experiment I suggest that you try to do is demonstrated in these two graphs. What you can try to do is do what's called a tuning curve. Most AFM systems have the ability for you to take the cantilever away from the sample, sweep the drive frequency from below resonance to above resonance, and plot the phase of the response as a function of frequency. Now, as we've seen before, if you're plotting phase lag, the phase lag as a function of drive frequency behaves as shown on the left, that it slowly increases and saturates at a value of 180 degrees. On the other hand, if your system is plotting phase lead, then its response is more like shown on the right-hand side, where it starts at a large value and then goes down to negative 180 degrees when you go above resonance. So by looking at whether the system plots this kind of a response shown on the left or the kind of response shown on the right, you can figure out or validate for yourselves if your system indeed is plotting phase lead or phase lag. Another thing is, if you're using somewhat old AFM systems, sometimes they don't even plot the phase in terms of degrees or in radians. It's in terms of millivolts. So how would you convert that into degrees or radians? And you get to that by realizing that when you do this tuning curve, whether you do phase lead or phase lag, the range of phase change that happens when you start from nearly zero frequency to going above resonance is 180 degrees. So if you're measuring the phase, or if your system is giving you an answer in millivolts, you can take the range that you see in millivolts and equate it to 180 degrees as you go across the resonance, and you can use that to convert the measured millivolts in phase into degrees. And with that, I'd like to conclude, and thank you.